Local time on each meridian is unique and directly depends on its geographic longitude. Universal time is measured at the Greenwich meridian and serves as a single standard for the entire planet. The zone time system divides the globe into 24 zones for everyday convenience. Shifting clock hands to daylight saving time helps efficiently use daylight and save energy.
Welcome. Today we are going to conduct a rigorous examination of the systems we use to measure time, starting from first principles, the rotation of our planet. As you can see in this animation, the Earth rotates against a backdrop of stars, and that line between day and night, the Terminator, visibly sweeps across the continents. This constant, predictable motion is the physical basis for all of our timekeeping. We're going to proceed deductively, building our understanding from the most fundamental physical concept all the way up to the complex, practical systems that govern our daily lives. We'll begin with local time, then move to universal time, zone time, and finally, daylight savings time. Okay, let's dive in. Our analysis begins with the most direct consequence of the Earth's rotation, the concept of local time.
So I want you to imagine a single glowing line running from the North Pole to the South Pole on this globe. That's a geographical meridian. For any observer standing anywhere on this line, the position of the sun in the sky, and therefore the time of day, is exactly the same at any given moment.
Now, this relationship between time and place isn't just an idea, it's expressed mathematically. Let's see how this builds.
What's really interesting here is how we can visualize this. On our globe, you can see two meridians highlighted. As the planet rotates, the individual times at each meridian are constantly changing, of course, but the difference between them remains constant. That difference in time perfectly equals the physical angular separation, the difference in longitude between them. You see, local time is precise, but it's also unique to every single meridian. This creates a clear need for a common reference point, and this led to the establishment of a global standard. By international agreement, this specific meridian, with a longitude of 0, became the anchor for global timekeeping. You can see the Greenwich meridian here, glowing with a distinct color. It is our universal baseline.
And so, the crucial point is that any local time on the planet can be precisely calculated from this single reference. Tm is the local mean time, T0 is universal time, and lambda represents the longitude of the location expressed in units of time and positive to the east of Greenwich. This brilliantly illustrates the direct mathematical link between time and your spatial position on the globe.
So, while local and universal time are astronomically sound, they're quite impractical for daily life. A different solution was required for societal coordination. Well, think about it. If we use pure local time, every town would have a slightly different time from its neighbor. That would create absolute chaos for travel and communication. And if we all used universal time, the sun would only be at its highest point at noon in Greenwich. That simply doesn't work for daily life elsewhere. The solution, proposed in 1884, was to divide the world into this number of principal sections. You can see how the chaotic map of countless meridians instantly simplifies into 24 clean, colored bands. These are our time zones. Each of these zones is approximately 15 degrees of longitude wide. All the clocks within one of these bands are synchronized to the local mean time of its central meridian. This is what creates large, practical areas of uniform time. The relationship back to universal time is remarkably straightforward. The zone time, T sub n, is just universal time plus the number of the zone n. That n simply represents the longitude of its central meridian in hours, counted east from Greenwich. This table really clarifies the distinct roles of each system. You have local mean time, which is physically precise and used for astronomical observation. Then there's universal time, our global constant for scientific reference. And finally, you have zone time, a practical compromise that allows civilization to function.
Finally, we'll examine a modern, non-astronomical adjustment to our timekeeping system.
Now, it's very important to understand that this is not a change to the fundamental time system. It is a legislated shift of the clock relative to that system. You can see the hands of the clock here just jumping forward by 1 hour.
The primary motivations are economic and practical. The whole idea is to better align our waking hours with daylight hours. The theory is that this reduces energy consumption that would otherwise be used for lighting in the evenings.
So we've gone from the Earth's rotation to global commerce and high-frequency trading. Our systems of time have clearly evolved to meet our needs. But the question remains, what will the needs of the future demand?
As we rely more on satellite networks and even atomic clocks, you have to wonder if our current system is the limit of precision, or if a new standard will eventually be required.
Thank you, friends. Strive for understanding and become wiser. See you soon.